Okay, so I'm gonna solve this problem from the 2021 class mechanics subject exam about the moment of inertia tensor of a cone. So consider a homogeneous upside down cone with base radius r, height h, and mass m. Choose the tip of the cone as the origin of the coordinate system. Its mass density distribution can be parameterized as this thing. So number one, compute the volume interval of equation 6 in order to show that C is equal to 3m divided by pi r cubed r squared h. Just make sure everything is working properly. Okay. So if we integrate the volume, the density distribution over all the volume, that should just give us m. So m is equal to the uh, density distribution times dV. So because this cone has cylindrical symmetry, we're going to use cylindrical coordinates. So the volume element in cylindrical coordinates is given by rho d phi d z. And so this is technically an integral over all space, but these heaviside functions are going to set the bounds of our integral. So to write that out just formally once, this rho goes from 0 to infinity, phi goes from 0 to 2 pi, and z goes from negative infinity to infinity. So that is all space in cylindrical coordinates. And then yeah, so C, right. So rho is gonna go, or let's do z first. So z is gonna go from 0 to h. That's our z integral. Phi is still gonna go from 0 to 2 pi, and rho is gonna go from 0 to r h times z. So that's what these heaviside functions do. So what's actually left inside the integral? You have a c, which is a constant, so that can go outside of the integrals. We just have a rho left from the volume integral, volume element. Yeah, so this is actually a pretty easy integral. Now that we have these bounds set correctly, so we have c. Let's just do it from the inside out. So rho d rho integrate over rho gives you rho squared from this to 0, so that's r over h times z squared over 2. So we can pull out some of the stuff again that's constant. So we have a c r squared divided by h squared by 2. And then this next integral, there's no phi dependence, so that's just going to give us a 2 pi. And then what's left is 0 to h z squared dz. So let's get some stuff. We have c r squared h squared pi. This is going to give us z cubed divided by 3. So that's okay. So that's equal to m. now we just have to, let's see, this can cancel. We just have to solve this now for C. So C is equal to 3 divided by I r squared h. Let's see. And that's what it says there. So that's the first part. So that will be useful later on in the problem. Okay, so the second part, which is a lot harder than the first part, is computing the complete moment of inertia tensor of the cone for rotations around axes through the tip. So the origin is already centered at the tip, so we can just use the normal, let's see, formula. So we can just use this formula. Um, for the individual components of the moment inertia tensor. The full tensor, which is actually a 3 by 3 matrix, so that's why I put this bar over it, is going to look like this: x, x, y, x, z, y, x, y, y, z. Sorry about this line here. Y, z. Sorry. This is what is this? Is z, x, z, y, easy. Okay, so these individual components are given by this formula, and this is the complete moment of inertia tensor. So let's just start with this first one, Ixx. So if x, so if I is equal to x and j is equal to x, that means I is equal to j, which means the Dirac delta function gives us 1. And this is going to give us an x squared. So we have the density, we have an r squared because the delta function hits, then we have an x squared here, and then we have the volume element. So that's Ixx. To actually solve this, we're going to use cylindrical coordinates again. So r squared minus x squared is equal to x squared plus y squared plus z squared minus x squared gives you y squared plus z squared, which in cylindrical coordinates is equal to rho sine squared plus z. I guess I can quickly show what, in case you forgot what cylindrical coordinates look like. If you have r uh, Z, you have an angle here, phi, and this projection on the xy plane is rho. So you have x is equal to um rho cos phi, y is equal to rho sine phi, and z is just equal to z. Okay, so that gives us this part here, and this these Heaviside functions are again going to set our limits of the integral in the same way. So what does that mean? That means that Ixx is equal to the same limits here. We have 0, 0 to h for z, then we have 0 to 2 pi, and we have 0 to r divided by h times z. And then what we're left with inside of the integral is the c. Then we have this thing here from the formula for the moment of inertia tensor formula. So we have rho squared sine squared phi plus z squared times the volume element again, which is rho d rho d phi dz. Okay. Just everything is correct up to this point. Yeah, looks good. So C can come. So we have a rho cubed here, so that's gonna give us rho to the fourth divided by 4. So it's r h z to the fourth. That's just this first part. That's rho cubed, integrate over rho cubed gives you rho to the fourth divided by 4. Then you plug in the limit, and then the second part you have a z squared times rho squared divided by 2. So plug in the limits, r h z squared d5 z. Okay, just simplify this. Oops, let's see, I made a mistake. I forgot this sign. There's a sine squared phi. So let me just rewrite this line in a little more organized way. So we have 1/4 r to the fourth divided by h to the fourth times z to the fourth times sine squared phi, plus we have r squared h squared z to the fourth, and this one has no phi dependence, d phi dz. Okay, now the next step is to solve the phi integral. So let's do that. So we have the only phi dependence here is the sine squared phi, and then the second term doesn't have a phi dependence. So the integral over phi for this term here is just going to give us 2 pi, and then this term here is going to give us the integral from 0 to 2 pi sine squared phi d5, which is just equal to pi. If you don't believe me on this part, you can just, well, uh, use integralcalculator.com or Wolfram Alpha. This integral, because it's squared, everything is positive, so it's sine squared from 0 to 2 pi. It's 0 at all these spots because sine is 0, so it looks something like that. And the integral, the area under this, is equal to pi. So okay, so let's keep going. This is C, 0 to H. So we have all the stuff that was there. 4 e to the fourth. Now this just pi from that. Integral over phi plus r squared h squared z to the fourth times 2 pi there. And now we just have the integral over z. So what's left? Let's check again. Oh, we lost a there should be a 1 here because this was integrating this over rho, so that gives you rho squared divided by 2. So there should have been a 2 here. Sorry about that. Okay, and this. So 2 here, and that 2 would cancel with that. So we just have pi's. So okay, so z to the fourth gives you z to the fifth divided by 5, plug in the limit, gives you, put some brackets here, gives you h to the fifth divided by 5 plus same thing, or z to the fourth gives you h to the fifth divided by 5. Okay, so now we just have to uh, simplify this a little bit. We have almost there for ixx. We have 1/20th r to the fourth I h plus 1/5 r squared pi h cubed. Okay, that looks right. Now we're gonna plug in the c from earlier. So let's see if I can. No. Okay. So that c was equal to 3m pi h. If we multiply that through, okay, so this h cancels this, pi cancels this is r squared, then r squared. So the first term is just 3m r squared, no h, divided by 20. And the second term is plus 3. Okay, shouldn't cancel it. Is 3m r cancels, pi cancels. So get h squared divided by 5. Okay, so that's ixx. The units are the same on both terms. We both have they both have a mass times a length squared, so like kilogram times meter squared, which is the units of moment of inertia. So that's good. We can just simplify this a little more. We can pull out 3m20, that gives us r squared plus 4h squared. Okay, so that's ixx. Now, that is only one of the terms, and we have to do 9 total, so 8 more. And that sounds like a lot of work, but a lot of these are going to end up being 0, so it's not uh, as hard as it seems. But let's move on to I, so this is gonna be is gonna be now r squared minus y squared. So we're gonna have a similar integral. The only difference is we're gonna have here instead of the y, we're gonna have minus the y, so it's actually just gonna be the integral right, so it's gonna be r squared minus y squared dv, which is gonna be equal to x squared plus y squared plus z squared minus y squared, so it's gonna be x squared plus z squared. So it's very similar to ixx. In fact, so x squared in cylindrical coordinates is gonna be rho cosine square phi plus z squared. And transforming this again into our triple integral with the correct boundary limits is 0 to h, 0 to 2 pi, and 0 to r divided by h times y, rho squared cosine squared phi plus z squared times rho c, forgot the c, d rho d phi dz. Now, this is almost exactly the same as ixx, except for the sine squared. Now we have a cosine squared here. However, the integral over 0 to 2 pi cosine squared phi is exactly the same as integrating sine squared, just also equal to pi. So this integral here, sine squared phi, is the exact same as cosine squared phi, which means that, okay, so you could do this integral over rho first if you wanted to, and then, okay, so let's just do one more step. So we get c 2 pi rho cubed over 3, so you get rho cubed, so rho to the fourth divided by 4, so 1/4 r z to the fourth times cosine squared phi there now, plus z squared rho squared divided by 2, so d phi dz. Now, so all these parts are exactly the same, like I said, except for the cosine, but because this integral is the same, we're going to get the exact same answer. So that means that Iyy is equal to Ixx. So that's two of them now because of that simplification. So we're going to continue on with the third diagonal one because you'll see all the off diagonal ones are going to have a nice trick also related to the phi integral. That's, we'll see. So let's do IZZ real quick. So that is equal to, let's go all the way back to the formula quickly. So r squared, because I is equal to j again, z is equal to z, so this will give us 1. And then we have minus z squared, so r squared minus z squared is going to give us x squared plus y squared dv, and this will simplify very nicely because it's rho squared cosine squared phi plus rho squared sine squared phi which is equal to just rho squared, because cosine squared plus sine squared is equal to 1 after you pull the rho square it out. So setting the limits again. Okay, so this part gives us a rho squared, the dv gives us another rho, and then d rho d phi z. Okay, now so this one is actually a lot simpler than the other ones. There's no phi dependence at all. So all we have to do, so you can actually do that one just quickly already. There's no phi dependence, so you can do these integrals in any order, but I like to do them from the inside out typically, but because I can see that there's no phi dependence already, I just do that one quickly. So we have rho cubed is going to give us rho to the fourth divided by 4. So that's, now we just have to do the z integral. 0 to pi, take the 4 out, take everything that doesn't depend on z out, so we just left with z to the fourth, so that's z to the fifth divided by 5, plug in the limits, gives you h to the fifth. Okay, so that's z. Just do some quick simplifications. We have h to the fourth, h to the fifth. We have 4 times 5 is 20, divided by 2 is 10, so we have c pi divided by 10 r to the fourth times h. And then we're going to plug in c again. Right, it's equal to 3n pi r squared h. I'm going a little too fast now. This is r squared h. Okay, so what are we left with? This pi's canceled. This gives us a 2h cancel. We're left with 3m r squared divided by 10. And we can check again. This has the correct units again, which is good. So that's easy. Okay, so now we've found all 3 diagonal elements, which is good. And now technically we have 6 more elements to find in this tensor. But because the moment of inertia tensor is a diagonal matrix, we know that I the uh, corresponding off diagonal elements are will be the same. So that means that I x y is equal to I y x, and you can see that in the integrals too. But what that means is technically we have 6, but really we just have 3 because 2 of them will always be the same. So continue with the off diagonal elements. Still using the exact same problem, the exact same formula for the components, except now all of these delta functions here are going to be 0 because I is never going to be equal to j. So this part will always give you 0. So the r squared component is not going to be there. So it's always just going to be these 2 parts here. So if we want to solve for I xy, for example, that's just the integral over the density times now, up one more time. There's a negative sign there, so it's going to be 0 minus x times y times dv. And now this is where the phi integral is going to be really nice. So show you in time. We have c, then we have minus xy, which in cylindrical coordinates is going to be minus rho cosine phi times rho sine phi, and then dv is going to be rho d phi d rho d phi dz. And now usually I would do this rho integral first, but because of this very nice phi dependence, I'm going to do the phi integral first. So the only things that depend on phi are cosine phi, sine phi, and this is an odd function. So sine is an odd function, cosine is an even function, and we're integrating it over an even integral. So the answer to this integral is 0, which is nice because that means we don't have to do any of the other integrals. So let me just write that out really quick. So if you have an integral over an even integral, so 0 to 2 pi is an even uh, uh, integral to integrate over. So if you have odd function x dx, that's 0. If you have an even function times an odd function, that's an odd function, which is equal to 0. If you have two odd functions, that's an even function, which will not be 0. But because we're always dealing with sine, it's these integrals are going to be 0. And if not, I'll say that. But that makes solving the off-diagonal elements really easy. So ixy is equal to 0. And because we know it's a symmetric matrix, we know that iyx is also equal to 0. So that quickly eliminated these two, and you'll see that the other ones are going to be pretty easy too. So the next one we can do is ixz. That's going to be similar. We're going to have minus xz dv, and again, the only phi dependence in this integral is going to be the, so x is equal to rho cosine phi. Okay, I guess, hold on, now we actually have to be careful. Cosine is an even integral, yes, but we're going to see that this integral is actually also still 0 because, well, so yeah, this integral is just 0 because that's sine phi from 2 pi to 0, which is 0. Okay, so that means that this integral is also 0, which means that izx is also equal to 0. So now we're just going through these pretty fast. So the last one is, this is getting messy, but we have this one we need yz. So similar fashion, iz is equal to minus yz. And again, the only phi dependence is this integral, which is again equal to 0. So that's all the components now. So make sure you, if there's any of the three integrals that you see are you can identify easily as being 0, just do that one first, and then it'll make your life a lot easier when solving these integrals. So let's write the final moment of inertia tensor is equal to ixx and so ixx and iyy were actually equal to each other. They were both 3 r squared plus 4 squared zero, 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 0. And then the only one that was different and also non-zero was IZZ. Okay, so that is the complete moment of inertia tensor of a cone through its tip. So we answered number 1 and number 2 now. And now the next two parts of the problem are related to finding the moment of inertia tensor through its center of mass. So we found all of everything while rotating around this. So the cone can go like this around the axis. It can go spin around the z-axis, and it can spin around the y-axis. So now we want to answer the question is how does this all change if, well, first we have to find the center of mass, which is not very hard, but say the center of mass is something like this. We have to see how the moment of inertia tensor is going to change when we now rotate through its center of mass. So how will this change in a different frame? So the first thing we have to do is find the center of mass. So this problem, part 3 of the problem. So we're gonna have a vector, which is from our original coordinate system, which was at the tip 0, 0. We're gonna have some vector that I'm gonna call capital R, not capital R, that's already taken. I'm just gonna call little r subscript cm. So from the origin of our original coordinate system, where is the center of mass of the cone? And the way we're going to do that is we're going to find the individual components of this vector. So, and the way I'm going to define those is call them x, r. So don't confuse this with the bar I put on the matrix. These are just the coordinates of the center of mass of the cone. And the formula we use to find those coordinates, so in general, the formula is I R I bar is equal to something called mi over m. And the way this mi is defined is an integral over the coordinate of interest. So Ri times the density matrix R dV, and then this M is again just the volume over the density matrix R dV. But because we're dealing with a evenly distributed mass, so homogeneous density function, density distribution, this is always just going to be M. So really we can simplify this problem, this formula, just to be 1 over M times the integral Ri Pm. Yeah. So let's do that. So the first one we find is just x. So the x coordinate of the center of mass of the cone is equal to 1 over the mass of the cone times the integral of x And by now you should be getting pretty used to this. It's the same old trick every time. So x in uh, cylindrical coordinates again is r cosine phi, and then this dv is going to turn into the rho d phi dz, and then it's the same trick every single time. So the integral of cosine phi after setting the limits is equal to 0, which means that x is equal to 0, and a similar way y is going to be y which again is 0 because the integral of sine phi d5 from 0 to 2 pi is equal to 0. And that you probably could have guessed because, I mean, this cone is something like this, and it's perfectly centered on 0, 0, so it wouldn't make any sense if, you know, the x and y coordinates were like somewhere over here, like that's just wouldn't make any sense. What you can expect though is this cone has more mass this way, so I mean, don't expect z to be 0. It's the z bar, which is what we're going to find now. So z is equal to 1 over m times, yeah, z dv, and now because z is just z in cylindrical coordinates, it doesn't have that nice phi dependence, so we actually have to solve an integral for one. So we have 1 over this is again just like part 1 when we solved all the integrals. 2 5 0, the row gives us a c, and then there's a z from the formula, and then this is going to give us d rho, sorry, rho d phi dz. There's no phi dependence, so we can do the phi integral easily again. C is a constant. C, do the integral over rho, gives you rho squared divided by 2, which is r z squared dz. Pull everything out that doesn't depend on z, cancel out these 2's. Get m pi r squared h squared. So we get c cubed, which is equal to h to the 4th divided by 4. M is 2 squared. Okay, again, we have to plug in the c from the very first part of the problem, which I forgot what it was, but it's over here somewhere. So we c, sorry, plug in c. C is 3m pi r squared h times what's left, r squared h squared 4. Okay, pi cancels, m cancels, r squared cancels. We're left with 3/4 h. Okay, so what does that mean? That means that we have all 3 coordinates now. So we have r center mass is equal to x, y, z, which is equal to 0, 0, 3/4 h. Now, this already looks good because this has units of length, which is good because otherwise it wouldn't make any sense. So that means that if we draw our cone again and we define this cone to be h tall, that means that the center of mass of the cone is right there where that spot is 3/4 h. So that's the center of mass of our cone. Maybe you could have guessed that, but now we know for sure what it is using this formula. Okay, so that's, yeah, so let's just box that because that is the answer to number 3. Okay, now we have one more part of this problem, which is all the way back. Find the cone's principle of moment of inertia in the center of mass frame. So, like I said, we have to find this moment of inertia tensor now at the center of mass, which we just found. And to do that, we're going to use something called the parallel axis theorem, tensor generalization formula, which is a big, scary formula that is actually not very scary at all. So this formula says that if we have the moment of inertia component somewhere, which I'm going to call the tip, that's what we solved for already in the previous parts of the problem, that is equal to the moment of inertia in the center of mass frame plus the distance away from the center of mass. So let me just write it out first and then I'll try to explain it. So it looks a little scary, but all this means is if we have, use this picture, we have the moment of inertia tensor through the tip here, and we want to find the moment of inertia tensor through this point now, which the distance, the parallel distance that it is away from here, we found. It's that distance is, so that's what we're going to use to rearrange this formula and find the moment of inertia tensor now through the center of mass. So again, we have a delta Dirac function, and we know what the center of mass vector is. And if we look at this, the only parts that are going to be non-zero are the ones that move from the original coordinate origin to the new center of mass origin. So what does that mean? It means that, well, first of all, we can write out this is just the magnitude of this vector squared, which is just this because all the other components are 0. And then again, this will only pick out the diagonal elements, and then these are just the elements of this vector that we already have here. So for example, let's just do the first one because I think it will make more sense if I just do it. So I x of the tip, we have this already from the first part, and we want to solve for I x in the center of mass, right? So what do we have to do? We have to add this. So we're going to have this because x is equal to x. So we get a 1 from the delta rag function. We have this part here, which we just... And now our center of mass x is equal to 0. So these two parts just give us 0. So if we rewrite this, IXS center of mass is equal to IXX tip minus this thing here. And that's really, that's it. So now we just find this from from the second part of the problem. So that's just equal to 3m 20 r squared plus, and all we have to do now is subtract this. So again, it has the correct units, so that's 9h squared divided by 16, and that you can simplify into something that looks like this. So what do we have? We just have to group the like terms. So we have h and m. So we have, I mean, you could already leave it like this. So you can simplify this, and then the answer that I have here is, once you simplify this, is that really all you're doing is subtracting this distance from the component that we already found in the last problem, because that's the parallel distance we're moving away from that axis. That's, oops, that's why it's called the parallel axis theorem right there. And then, okay, we have to look if there's any other components. So the off diagonal elements are all 0 from this part, and then x, y is 0. Anything with x or y multiplied by something else is 0, because all the components of the vector besides z are 0. So the only other component that's non-zero is going to be yy, which is going to give you the same answer. So it's just the same as, and you can do just see the last diagonal element is ICZ, and that is equal to so z is equal to z, so you give it this first part, so you get c, so you get r squared minus zz, which zz is the only component that's non-zero again, so you get z squared minus z squared, so you get 0, which means that izz hip is equal to izz center of mass. And I guess now you can write this final tensor if you want. You can just This one is the same as before, and that's final answer. So if we look at this, these are exactly the same as through the tip, except there was a 4 here before, and now it's dividing by 4. So which means that these two components became smaller. So if you look at this picture, again, we're rotating now around the center of mass, which means there's less mass away from this point. So it's easier to rotate this around this point than it is this point. So I realize you can't see my pen. So it's easier to rotate this cone around this point because there's less mass to move. The mass is closer to this point than it is to this point. So that's kind of the intuition of to explain why these have become smaller and why this one didn't change, because that's rotating around the z-axis, which is still exactly the same as it was at this point. So these two became smaller, and this one remained the same. So that's all parts of this problem. So I hope this helped. Thank you for watching.